Good day, good people. Welcome back to MJ's Brain Boost. And in today's session, we are focusing on the electrochemistry, known as the electrolytic cell. If you haven't yet visited our video on the galvanic cell, you are more than welcome to visit that video on MJ's Brain Boost. So we're gonna focus on electroplating, aluminum extraction, copper purification, and how we decompose the solutions such as copper chloride and or sodium chloride. Please don't forget to like, share, comment, and hit the notification button below so that you get notified once we upload new content. Stay tuned. So the electrolysis, so basically in an electrolytic cell, the process is non-spontaneous. So it means that the it needs the external electrical energy from a DC power source. It could be a battery or power supply to make the chemical reactions happen. All right. So basically, you're using the electricity to break down the different compounds. So we've got the setup. Remember, with this one, we do not need the salt bridge. We only have one compartment, all right? And then we've got this power supply here, and then you still have got the cathode and the anode. But the cathode is where it's negative, and it's where reduction is taking place, and then anode is positive in this case, and it's where oxidation is taking place. And then we've got the electrolyte solution. You've got electrolyte solution, and the electricity is going to be passed through the solution. All right. So I want to bring to your attention that in this case, the positive terminal of the power supply is connected to the anode. All right, it's connected to the anode. The positive side is connected to the anode, and the negative terminal is connected to the cathode. So, and then these are that can be carbon, because carbon is preferred because it's less expensive. All right. And then the we want to also understand how the electrons are moving. All right. So we have got the real movement. So we know that the electrons are always moving from are always moving through the external, all right, are always moving through the wires, the external circuit, all right. We know that the electrons are always moving through the external circuit, which is wires, and it's always moving from the negative terminal to the positive terminal of the battery, all right. So what happens is they move from this negative terminal of the battery like this, all right, like that, and then through the cathode, then through the electrolyte solution, and then all the way to the anode, and then goes to the positive terminal. That's the electron flow, the real movement, all right? So you must remember that the battery, this battery pushes the electrons out of its negative terminal, and then these electrons will flow into the cathode, which is the negative electrode, and then at the cathode, we've got the positive ions. Okay, we've got positive ions, could be copper 2 plus or sodium plus, all right, in the solution that these would receive the electrons that are coming in. So the electrons that are coming in, they're going to be received by the at the cathode side by the positive ions, all right? And then when these positive ions are receiving these electrons, all right, these incoming electrons, reduction is taking place. So that's why at the cathode, that's where reduction is taking place. And then meanwhile, at the anode, we have got the anode is the positive electrode. So we are having the negative we're having the negative ions, for example, chlorine ions, which give up their electrons. Okay, so that's where the oxidation is taking place. So these electrons released at the anode would now go back to the battery's positive terminal. All right. But this was the electron movement. So we also have the what you call it, the conventional current flow. So this part, I know it confuses many people, because in science we know that in science, current, what do you call current? Current is set to flow from positive um, to negative. Okay, this is what you call conventional current. But electrons, they actually move in the opposite direction. That is to say, from negative to positive. So please don't confuse the conventional current with the movement of electrons. They are doing the opposite. All right. So I hope it makes sense, good people. So the electrolytic cell, like I said, we have the cathode and we've got the anode. All right. So the cathode is the negative electrode of the electrolytic cell. This is because it's connected to the negative terminal of the battery. And then the positive ions are attracted to the cathode, as I've explained, where they accept electrons and the reduction is taking place. Okay. So can you see that the cathode is connected to the negative terminal of the battery? The cathode is connected to the negative terminal of the battery. That's why it's negative instead. But the opposite is true for the anode. Anode is the positive electrode of the electrolytic cell because it's connected to the positive terminal of the battery. So electrons from negative ions are transferred to the cathode. All right, so electrons are given off and oxidation takes place at the anode, as I've explained over here, that here the oxidation is going to take place. Oxidation is going to take place because the electrons are given off. Then these electrons are going to go back, all right, there, like there. And then here, that's where a reduction is taking place. So the cathode, for electrolytic cell, reduction is taking place at the cathode, and the oxidation is taking place in the anode. So it means the electrons are received at the cathode, okay, electrode, and are given off at the anode electrode. This is the opposite of what the galvanic cell is doing. I hope it makes sense. So electrons are released from the anode and are accepted at the cathode. So the process of electrolysis is take place. All right, that is the you remember that the galvanic cell is spontaneous, so it means it happened on its own, so without the need for the power supply. All right, but this one needs the power supply, and this one, what does it do is it converts the electrical energy, all right, into the chemical energy. But for the galvanic cell, the that's where we are producing electricity. That is, we are converting the chemical energy back into even if we're not to say back, but chemical energy into electrical energy. All right. So we've got application of electrolysis. That's the main focus of our lesson today. So we're gonna focus on electroplating, extraction of aluminum, purification of copper, and decomposition of solutions such as copper chloride and sodium chloride. All right. So here we first start with the electrolysis of copper chloride. I want to start with this one. All right. So remember, electrolysis take place in a solution. All right. And that solution must conduct electricity. And then that is what we call electrolyte. So this blue is what we call an electrolyte. So in this case, electrolyte is copper chloride. All right. In this case, electrolyte, it will be copper chloride. In this case, we will have copper chloride. That's what we call our electrolyte. It means it's a solution. It's a solution that can conduct electricity. Okay. But now, interesting part is this electrolyte, it contains positively charged copper ions. All right. It contains the positively copper charged ions and negatively charged chloride ions. That is our electrolyte, right? So what happened is we also have got two inert, or if you don't want to say inert, you must say unreactive solid electrodes. These electrodes are inert. It means they are unreactive. So you can have the graphite. All right, you can choose to have graphite. If you don't want to say graphite, you can say carbon. Okay, you can choose to have these. Remember these ones, they are reasonable. They are not that costly. All right. But we can also have the electrodes. For example, platinum. But the platinum one, it's a little bit expensive. All right. So these electrodes, as you can see here, they are dipped into the into this solution, and they are connected. They are connected to a direct current or DC power supply. Okay. I hope it makes sense. But as I've mentioned, that the graphite, not the graphite, but the platinum, which works well, but the disadvantage is expensive. So that's why graphite is commonly used. So let's now say we're having this graphite connected to the DC. All right. So we are having one compartment and no what do you call this salt bridge. All right. We are just having one compartment. So what is happening? So these copper ions, they would move towards the negative electrode, which is the cathode. All right, they're moving to the negative electrode, which is the cathode. So the chloride ions, they would move towards the positive electrode, which is the anode, as shown here. So this movement of ions would allow the redox reaction to take place at each electrode. It means we are going to have half reaction this side and half reaction that side. I hope it makes sense. So now the copper copper is going to be deposited. That's why we say deposit of copper metal on an electrode surface. This brown material, the copper. Okay, because the positive ions are attracted to the negative electrode. That is to say, here we're going to be gaining. All right, we're going to be gaining electrons. So a reduction is taking place. All right, I hope it makes sense. So I want us to understand the half reaction that is taking place um, um, in each or at the cathode and at the anode. So let's check first at the cathode. Allow me to write here. So at the cathode, we are having these two or copper ions that the remember we are focusing on the cathode, so these will gain two electrons, all right, and to give us the solid copper. So this will be aqueous like that. So this is half reaction that is taking place at the anode, all right, at the cathode rather. All right. So, so why are we having this? Okay, we'll have this brown solid copper which forms. Okay, so or it's deposited on the cathode. All right. So this brown solid copper deposit on the cathode. That's how we are forming the copper. But at the anode, which is the positive electrode, so we have got these chloride ions, which lose electrons and are oxidized to form chlorine gas. So in this case, you will have chlorine ions, all right, which now they would lose two electrons, and they would lose two electrons to form this gas. They would lose two electrons to form this gas. So in this case, oxidation is taking place. In this case, reduction is taking place. But if you don't understand this one, for example, how this oxidation is taking place, I mean, you can say just that chemistry will avoid these negatives. But in simple terms, what's happening is we're having this, all right, and it's losing two of its electrons, all right, to form the chloride gas, all right, to form this chlorine gas. But if we were to take this to the left-hand side, you will still have this. All right. So in case you don't understand, but this would mean one and the same thing, but we prefer this one. All right. We prefer this one, positive ones. I hope it makes sense. So in summary, the copper deposit would take place at the negative electrode where we're having cathode half reaction. So if they were to ask you in the exam, write cathode half reaction, you will write this one. The anode half reaction would write this one. All right, that's what you call the the what do we call this, um the electrolysis of copper chloride. You are breaking down the copper chloride into its respective elements. So we're having this copper chloride, we had this copper chloride, and then we broke it down into its elements like this. So we are breaking it down using the electricity. Now, so if they were to say now, write the net reaction, what are you gonna have? So you'll say, well, we had this um the net reaction, all right. So you'll have, or the overall reaction, you'll have copper chloride, all right, in the aqueous, and then you are breaking it down to okay, copper solid plus chlorine gas. So this will be your overall reaction. That's why I'm saying that you are basically electrolysis of copper chloride. You are basically breaking down this compound using electricity to form its respective elements. So in this case, you will form copper as a copper solid, all right, and also the chlorine gas. Copper or solid copper, it will be formed at the cathode side, and then the chlorine gas, it will be formed at the anode side. All right, it will form this. So you'll see, you are also seeing these bubbles. So these bubbles are showing that this is a gas. All right, so I hope it makes sense. So this will be your overall net reaction, showing that you broken down this compound into its respective elements. So this is the summary of the electrolysis of copper chloride. We have copper positive, the cathode is a positive copper ions move to the cathode, all right, where they take up electrons and form the solid copper, which forms a reddish brown deposit on the cathode, all right. And then this is our half reaction that is taking place at the cathode side. And then the anode, the negative chloride ions move to the anode, where they give off electrons to form a chloride gas, all right. Anode half reaction is this one. So I hope it makes sense. So this one, we also have got the electrolysis of sodium chloride, all right, sodium chloride or table salt, all right, and it's molten, So you must understand that the electrolysis, don't forget that electrolysis, it's a process that uses electricity to break down a compound into its element. So in this case, we'll be breaking down the molten sodium chloride. So in this case, you are breaking down the molten sodium chloride into a sodium, all right, plus chlorine. All right, so you're breaking the compound into its respective element. That is what electrolysis is all about. But the molten in this case, it means the sodium chloride is melted. The molten means the sodium chloride is melted. So it means it's in liquid form, but not dissolved in most in water. So this is important to be understood because um, the sodium ions and chlorine ions are going to be present in the solution. So no water to interfere, right? I hope it makes sense. So this is our setup, exactly like what we saw previously. We're having two electrodes, one positive, which is anode, and one negative, which is cathode. All right. And we've got the molten sodium chloride in a container, and then we've got the power source like a battery, right? But now, what happens is the at the cathode side, that is the electrode or the negative electrode, you're going to have the attraction of positive ions. All right. So the cathode attracts positive ions. So sodium ions, it means they would gain electrons. That's where reduction is taking place, and they would become sodium metal. So it means now this is what's taking place. All right, at the cathode. All right. Now the anode, which is positive electrode. All right, the anode, which is the positive electrode here. Okay, remember this one is the anode, and this one is the cathode. So um, the anode would attract this chlorine or these negative ions. Okay, all right, and then it means that the chloride ions, they would lose the electrons. That's where oxidation is taking place and form the chloride, the chlorine gas. All right, so that's why you're having these. All right, form chlorine gas. But now this will be our net reaction. This will be our net reaction. It means we need to balance this first. You need to multiply both sides by 2 so that we have got same electrons. So on the other on either side. So you'll have this plus 2 electrons to give you 2 sodium. All right. And then this one will be 2 um and then to give you that and that. So this one and that one, they will cancel each other out. So that's why your net reaction now, it will be you'll be having this plus 2 that to give you so this will be your net reaction. All right, I hope it makes sense. So you need to understand what's happening at the anode and what's happening at the cathode. So this is electrolysis of salt. So it means the final product at the cathode, you'll have sodium metal. All right, you'll have the sodium metal, which is a silver solid at the cathode side. All right, you'll have silvery solid sodium metal, and then at the anode, all right, at the anode, you'll have this chlorine gas, okay, which is greenish to yellowish gas, and then that's why you see these bubbles. You see these bubbles. So piece of advice is always and have this in your mind. What what's happening at the cathode, what's happening at the anode. Know these things and understand them. So because in the exam they might not, that they won't tell you that this is anode or this is cathode, but they might show them, they can just show you the movement of these negative and positive ions, and then they said which one is the anode, which one is the cathode, and what's taking place at the anode, what's taking place at the anode. So you must always I understand that. So we also have got the purification of copper. Okay, so um, don't forget that this is electrolytic. All right. So let's talk about the purification of copper. So I need to tell you, or to bring to attention that um, remember, to purify is to make something to be clean. All right. So we know that the copper ore. So when we are mining copper, all right. So remember, I like these you know copper ores and extraction of aluminum because I'm a geologist by profession, which is why I like these things even more. Okay. But when we mine copper, the copper, it wouldn't be clean. It would be, it will be having some impurities. So your job is to remove these impurities so that we are left with the clean copper. So this is basically the job of what you call the metallurgist. So to those of you who would like to pursue the career in the metallurgy or in the geology, or in geology, you'll be doing what we call the um um especially what you call the what do we call this? Why do I forget this discipline? Not extractive metallurgy. Yeah, metallurgy is extractive metallurgy, but for geology is what do we call this? Yo, I forgot this. I forgot this, but it will come back just now. Yes. Um, Mineral processing. Yes, mineral processing. Thank you. All right. So basically, you need to not just cram this from passing your grade 11 or grade 12, but also to understand that these you'll apply them once you be at the workplace. So, um, at for purification of copper. And so you'll be having the anode side, you'll having the impure copper, that is, say, the one that is dirty, all right, the one that needs to be cleaned. And the cathode, you'll have the pure copper, that is the clean one, all right. And that's what will happen. So the solution, now you'll have copper sulfate, all right. So it helps move copper ions around. So what happens is at the anode, copper ions break apart and becomes copper ions. All right. So you're having this copper, which is impure. All right, which is impure. All right, at the anode, or the one that needs to be purified. All right. So what it breaks down, it breaks down to give you more of copper ions, and then releases these electrons. All right. So it means at the anode side, you are producing more of copper 2 plus. You are releasing them, right? You are releasing them. So, but now these ones, they would now be they will be moving in the solution because of the help of electricity. Moving to what? To which side? They would be moving um to the cathode, all right, to the cathode side. So the cathode side, what happens is now the copper ions from the solution, they would now be sticking to the cathode and become solid copper. So it means in this case, the copper 2 plus that were in solution, they would receive a 2 or they will receive electrons then to form more of the copper solid. Then now that's why this one now it will be pure. So that's why the cathode, it will be the pure one that we have just formed. I hope it makes sense. So let's understand this looking at this diagram. So can you see that um, 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 we're having the cathode where a reduction is taking place, and we're having the anode where the oxidation is taking place. So at the anode, that's where you're having impure copper, all right? And then you're breaking it down to give us copper ions. So these copper ions enter into the solution, and then they would now go into this. They would go into this section, and then now this copper 2 plus from the solution, they would now remember the electrons they've been released. The electrons have been released, then they're coming in. Then now these electrons are here. So the 2 plus ions that were in solution, like receiving electrons that were released by the anode, these electrons that were released at the anode side, and then that's where a gaining is taking place, a reduction is taking place to form us or to give us copper solid. All right, to give us copper solid. Remember, you're purifying copper. Then this one is the one that is purified, and then it means that this side, the cathode, it will get bigger and bigger, okay, because your pure copper is building up, pure copper is building up. But this one, because you're breaking down, you're breaking down the impure copper, all right, or you're dissolving it, all right, with the help of electricity. So it will get the anode, it will get smaller and smaller, all right. But one thing that we must always know is the solution must stay balanced. All right. So it means the copper that are getting into the solution must be equal to the copper that we are using up to form copper solids. All right. I hope it makes sense. All right. But now we also have got this sludge, right? We also have the sludge. So these are the valuable metals like silver or gold that collect below the anode, right? This one. This is what you call the sludge. All right. So I want to bring to attention that um what do you call the impurities, how we get this sludge. So we're having impurities, all right? So impurities, you'll be having reactive less reactive metals, for example, silver or gold. All right, gold. All right, so these ones will fall off and form a sludge. Is this one? Okay, these are the impurities, but we also have got other impurities which are more reactive metals. Okay, for example, zinc. So these are more reactive. So these ones, they would dissolve, dissolve into the solution with those copper 2 plus ions, with the solutions, okay, as ions. So it means you'll be having zinc 2 plus, okay. Remember, to be in a solution, it means the metal must be in ionic state. All right. So these are the impurities. The more reactive ones, they would enter into a solution, but the less reactive ones, they won't be able, because they are less reactive. All right. They will fall off and then form this sludge. So it means this sludge, could be silver or gold. But we start to have a little bit of a problem, because with the time, zinc ions from the impurities, they build up in this solution. So it means if too many are present in this solution, they might start depositing instead of a copper. But remember, we want to deposit copper, not zinc. All right. So it means now with the time, we can start to deposit zinc. So it becomes a challenge. So it means now these copper sulfate, all right, solution is copper sulfate solution, all right, the copper sulfate solution must be cleaned. The copper sulfate solution must be cleaned regularly so that our reaction does not give us a problem, but we keep on producing more of the pure copper. Remember, in at the processing plant, all right, in the industry, they focus on making profit. All right, they focus on making profit, but in the process of making profit, they must always make sure that they are not using more of the electricity, right? But producing less money. So that is the focus, right? So I hope this it makes sense. Purification of copper. All right. So let's talk now about the electroplating. I mean, you guys have spoons, your earrings, your rings, and so many other things. All right. Um, so um, so electroplating, basically what's happening is you are basically covering, all right. So you are covering, you are covering the metal that is expensive. All right, you are covering with the metal that is expensive. All right. So, for example, when you are electroplating with let's say gold, all right. So it means at the bottom, and the bottom layer could be, let's say, silver. Then you are coming with gold. So it means now this one is electroplating. So you're coming in with gold. So it means at the bottom you are having the layer of silver, but at the top you are having the layer of gold. All right. So that is electroplating. So that's why we say during the process of electroplating, one metal, now is this silver, is covered with a layer of another metal, which is now gold. All right. All right. But for your spoons, usually we see this or basically many cutleries, we see this silver. So the aim of electroplating is to protect against corrosion, all right? Is to protect against corrosion. For example, we know that iron, when it's oxidized, exposed to oxygen, usually it corrodes. So usually they need to be, electroplated. So again, for example, with chromium, because chromium in mineralogy, in geology, we say it withstand high temperatures, all right, and it withstand corrosions, all right? So, hope it makes sense. So, electroplating with zinc is called galvanization. So, it is mainly used to protect steel. So, you can electroplate that with zinc, and we call it galvanization. So, other examples include chromium, silver, and gold. All right, you can tell gold rings and other things. All right. Um, because they know that pure gold is going to be very, very expensive to buy that ring or that necklace or whatever. So we electroplate it so that it becomes at least reasonable. All right. So chromium is used in motor spares, whereas silver is used in cutleries. So let's talk about the electroplating with silver. All right. So this is the setup. This is the setup. We having still having sorry about that, the battery, and then we're still having um um okay, we're still having our electrolyte. In this case, we're having the nitrate. I always tell you that the nitrate are soluble, so we always prefer them. So we're having silver nitrate electrolyte. So the um the the material that we want to cover or electroplate, we put it at the side, at the negative terminal of the battery. All right. So, and the material that we want to get for example, if we want to get the silver or zinc or any gold, we putting that at the and a positive side of the battery. All right. So, but what's happening is oxidation and reduction here, they will be taking place simultaneously. All right. So the anode is the silver metal. The anode is going to be silver metal. So this will be your anode, and this will be your cathode. Remember, the cathode is the negative electrode, and it's connected to the negative side of the battery. All right. So and then the cathode, that's where you put the object you want to coat, in this spoon. All right. And then the solution is this silver nitrate. So what happens is at the anode, we are having these silver atoms. Okay, they will become you're breaking them down. All right, you're breaking them down to form silver ions. So you're bringing in more of silver ions into a solution. But at the same time, simultaneously, these silver ions that used up, all right, to form silver solids. So the cathode, silver ions become solid silver. Okay, so it means the silver leaves the anode and sticks to the cathode. That is, you're coating it. So basically, this is the idea about the coating. The silver ions, they would leave they would leave the anode and stick to the cathode where they where this coating this. All right. So if they say, give us, you must know these things by head. That what's happening at the anode and what's happening at the cathode. So at the anode, like we said, the silver solid, okay, it breaks down to give us more of the silver ions. Then at the cathode, and so at the cathode, the silver ions, we are using the silver ions that that we produced from the anode side. These silver ions, they are used, all right. Then they are receiving the electrons to give us silver ion. The silver solid that is coating. So that's why here a reduction is taking place here. Reduction is taking place, and this one, oxidation, is taking place because we are giving off the electron. Then here we are gaining electrons. Then that is basically coating. And then now after that, you can still have the net reaction. So you can still have the net reaction. All right. Can have that plus that to give you silver solid. Okay, so this will be the aqueous, sorry, and this will be the aqueous. So we've got, this is balanced, the electron on this side will cancel the electron on that other side. So then you will have a silver solid plus this aqueous one to give you um okay. All right, solid. Aqueous. Sorry. Can write aqueous. All right. So this could be the net reaction. All right, it could be the net reaction, but obviously they will cancel each other out. They will cancel each other out, as you can see over here. I just wanted to show you that these ones, so you can cancel them, but obviously even these ones, they would now cancel each other out because you have aqueous this side, aqueous that side. Remember, this one is the solid. Okay, this one is the solid, this one is the aqueous. So they will end up canceling each other out like that. Then we also have what do you call this? The extraction of aluminium. We also have got extraction of aluminium. So this is important stuff. Aluminium is found in rocks as a compound called a bauxite. So bauxite, usually in geology, we say closer to the surface of the earth. If this is the surface of the earth, usually the bauxite will form closer to the surface of the earth because that's where oxidation is taking place. That's where oxygen, remember, you are closer to the surface of the earth. That's where oxidation is taking place. That's why we are having this reddish material, right? So I hope it makes sense. So to get a pure aluminum metal, we need to break it apart, and that takes the electricity. So we use a process called electrolysis, just like copper purification, but with a twist. Okay. So setup, we need to have electrolyte, that is molten aluminum oxide mixed with cryolite to lower the melting point. So cryolite helps reduce the cryolite helps reduce energy cost by lowering the melting point of aluminum oxide. I told you that in the processing plant that they care about, making money. So, and then we also have got the carbon anodes, which wear out over time because they react with oxygen. So they would need to be replaced more often. All right, the carbon anodes, they would need to get to be replaced more often. So this process, we know that it uses lot and lot of electricity. So that's why, ladies and gentlemen, aluminium is very expensive to extract because this process, it uses lot of electricity. Okay. So I hope it makes sense, and I hope it makes sense that aluminium is found in rock, in a rock, for example, this one. All right. So from bauxite, we get aluminium oxide. All right. From this bauxite, we're getting the aluminium oxide, but it's very hard to break apart. Okay. I hope it makes sense. So that's what's happening. Let's break it down. So aluminium oxide, aluminium. All right. This one. Um, It melts at temperatures of about 2000 degrees Celsius. That is super hot and is very expensive. All right. So then we mix it with the cryolite, this aluminum oxide. We mix it with cryolite. Cryolite is sodium 3, aluminum, then F6. That is cryolite. Cryolite, it melts at 900 degrees Celsius. So it means that this cryolite, it will lower the temperature of the it will lower the temperature of this aluminum oxide to about 950 degrees Celsius. All right. Now it saves energy and money. Then now it saves energy and money. So, but from this setup, we're having this container, all right? We're having steel tank. This steel tank is lined with carbon. Okay, so this carbon acts as the cathode. So this carbon, it acts as the cathode. So this will be the cathode, is the lining, all right? So electrodes, we're still having both anode and cathode, all right? And they are made up of carbon or the graphite, all right? They're made up of carbon or the graphite, all right? So this is the cathode, all right? And this is the anode, which is carbon example, for example, both the electrodes, they are graphites. All right, but the cathode, it acts as the lining, like that. All right, so electrolyte, it will be the mixture of aluminum oxide. So it will be the mixture of aluminum oxide and molten cryolite, which reduces the melting temperature, All right, I hope it makes sense. So it means this is the setup, and you must always understand it. But you need to understand what happens during electrolysis now. All right. At the cathode, all right, that's where we're having this carbon lining. We will have this, all right, this part will have this aluminum 3 plus ions, which they gain electrons and they will become aluminum metal. All right, that is the reaction that is taking place at the cathode. All right, so it means now aluminum would now sink to the bottom and it will going to be collected. All right, because you are forming more of aluminum, and now it becomes heavy. Aluminum, become heavy, heavier than the solution, and then it will settle at the bottom. That is the molten aluminum collected at the bottom here. Because it's heavier than the solution, then it will settle at the bottom. This is this one. Then at the anode, positive, all right, at the anode, remember this happened this side, and then this one, it will happen that side. All right, so um at the anode, we're having oxygen ions which lose electrons and become oxygen gas. So this is the reaction. They get to be oxidized and become oxygen gas. So it means oxygen react with the carbon anode, all right, and then they form the carbon dioxide. I hope it makes sense. I hope it makes sense. So it means now oxygen, in this case, oxygen gas is going to be released, but it will react with the carbon anode. This oxygen, it will react with the carbon anode, and then they form the carbon dioxide. I hope it makes sense. All right, but I want to I want to bring to your attention, all right, how we are going to have the net reaction. All right, don't forget that we started with aluminum oxide. Okay, and aluminum oxide, what does it contain? It contains aluminum ions plus this. Remember, this was derived from this, right? So we are having this from that. So it means during electrolysis, these ions are separated using electricity. So you are separating these ions using electricity. But at the cathode, that is the negative electrode, at the cathode, the negative electrode, this one, okay? Aluminium 3 plus, okay? They gain electrons to give you aluminium, and this aluminium, it will settle at the bottom. But since each aluminium oxide has 2 aluminium atoms, it means we need, all right? Remember, each aluminium oxide has 2 aluminium atoms. Can you see? We've got 2 aluminium atoms. So therefore, it means we need 4 aluminium 3 plus ions to make 4 aluminium atoms. All right, I hope it makes sense. But at the anode side, oxygen ions lose electrons and become oxygen gas. Then we're having this. All right. I hope it makes sense. And each aluminum oxide, how many oxygen does it have? Oxygen atoms does it have? It comprises 3 oxygen atoms. All right. So it means, what do we need? So it means 2 aluminum. It means these 2 aluminum oxide will give you 6 oxygen atoms. It will give you 6 oxygen atoms. So these combine, when combined, they will form 3 that molecules. Okay. Now let's put everything all together. All right. Now it means from aluminium oxide, we get 4 aluminium atoms at the cathode. And then we also get 3 oxygen molecules at the anode. So now, I hope it makes sense. Let's now make or come up with the overall reaction or net reaction. Then now it would mean we are having 2 aluminium oxide to give you 4 aluminium plus 3 that. This will be our overall net reaction. This would be our overall net reaction. I hope everything makes sense, ladies and gentlemen. And this will bring us to the end of our lesson today. If you enjoyed this lesson, please subscribe to our content, and if you are still struggling with some of the concept, you are more than welcome to comment in the comment section, and we will be pleased to attend to your question as soon as we get the message. So as you are practicing for the exams, or for the test, or any other preparations, even for electrochemistry, remember, also for metallurgy students, they are still doing this electrochemistry. So it doesn't matter if you are a electrochemistry student or a metallurgist student. This is also good for you. All right, this is also good for you, so to learn the very basics of this electrochemistry. I hope it makes sense. So please, ladies and gentlemen, do not try to cram this. Do not try to cram this. Try to understand everything here. Don't try to cram this. All right? Don't try to cram this. Make sense out of these things. Make sense out of these things. Understand them. Understand them. I always tell people that if you cram, it will be difficult for you to understand, all right, what the examiner want. But if you understand the processes, all right, then it is going to be easy. Okay. So please read and read very, very, very hard. All right. And if you're still struggling, please always comment on the comment section, and I will be pleased to to um clarify some of the concept. So with that being said, let's I think this will bring us to the end of our lesson, and please comment on the comment section on the chapter that you also prefer. Please comment on the comment section on the chapters that you also prefer, and I will be pleased to assist you. And as we no, oh no, guys, before we no, we cannot do it this way. Sorry about that. Before we all right, for our net reaction. So we cannot do that. I was surprised why I did it that way. So you cannot do the reaction, the net reaction of this thing like that. So you would need the oxidation of water. For you to come up with the net reaction, you will need the oxidation of you will need the oxidation of water. For example, you would need H2O, a liquid, and then to give you this. Sorry about that. And 4 electrons. You'll need the oxidation of this, so that now you can multiply. Remember, this will be the oxidation of water, all right, and then the cathode side, the cathode side will be having this, the aqueous plus electrons, to give you this, right? This is what's happening at the cathode, and this is what's happening at the anode. And then you can multiply the cathode half reaction by 4 and add this, right, add this material. Then it means now, at the end of the day, you're going to have 4 aqueous plus 2H2O liquid, and you can have 4 solid plus O2 is all right, plus 4. All right. So I hope it makes sense. I hope it makes sense. Just so, but for matric and grade 11s, it's not necessary to know how to find the net reaction using the um using the oxidation of water, but yeah, don't stress about that, so let's call it a night or a day, but you know what I'm about to say. Until next time, cheers.